So today I'm going to share a TESS discovery of a sub-Neptune orbiting a mid-M dwarf TOI-2136. So up to date, there are over 5,000 planets discovered so far, but you can see that most of the planets do not look like any of the planets in our solar system, specifically speaking about the super-Earth and the Neptune-like, or the sub-Neptunes. So they are planets with a mass between Earth and Neptune, with a radius between 1 to 4 Earth radius. They look very similar, but in fact, they have very different composition and density. Thanks to the discovery of radius valley, or the radius gap, we can easily distinguish between the super-Earth and the sub-Neptunes. So here is a figure illustrating the location of the radius valley. The black dashed line here are representing the radius valley for planet orbiting sun-like stars, where it can be predicted by a power law function. As you can see here, it has a negative slope, so we have a negative value on the exponential. However, the black solid line, this one, is also illustrating the radius valley, but for a small planet orbiting a low mass star. The relation between the radius and period could be predicted by this equation. So as you can see here, it has a positive exponent, meaning the slope of it is positive. So these two scenarios could be predicted from two different formation mechanisms. So the first one, for planet orbiting sun-like star, it could be predicted by the thermally driven photo-evaporation model, which states that the super-Earth are formed from the core of some Neptunes, but with the gas envelope being stripped by photo-evaporation. And then the second scenario, it could be predicted by the gas pole formation model, where it supports that the super-Earth are formed late, where the gas in the parent gas disk were about to be cleared. So which one would be the dominant mechanism in the low mass regime? We still have no idea yet due to the very small sample population we have for the small planet orbiting low mass stars. So the discovery of the TOI-2136 system, as I'm going to share in the later presentation, falls perfectly into this category. So it helps to populate the sample population we are interested in, and hopefully with more and more exoplanets fall into this category are being discovered, we will have a better understanding of the dominant formation mechanism. So in the discovery of the TOI-2136 system, three main methods were mainly employed. So they are the space and ground-based photometry, high angular resolution imaging, and also the radial velocity measurement. So for the photometry part, the transit of TOI-2136b, the planet, was first observed by TESS in 2020, and it was reobserved a year later in the extended mission, also by TESS. And here it is a sample detrended TESS light curve of the whole star, and especially each transit of the planet is highlighted with the red dots. So due to the large pixel scale of TESS, we are not sure. We can't just validate the presence of the planet just based on their light curve, since eclipsing binaries could be also one of the false positive stars that could cause a transit signal. So to further validate the existence of the planet and to rule out the false positive caused by eclipsing binaries, the follow-up ground-based photometries and high-resolution images were taken. So finally, after all these processes, the authors were able to conclude that the transit is on target and there is no companion around TOI-2136. So this basically ruled out the possibility of a false positive and also prove the existence of the planet. Also, radial velocities were also taken and through the line-by-line method and analyzed through multiple coding packages, such as TOI-RV or rad-val in this case. So what is line-by-line method? It is a method that derives radial velocity by dividing a spectrum into a large number of lines and projecting the residuals between the template and the spectrum onto a first derivative template. So this basically provides a per line velocity, and the mean radial velocity could be further calculated from that. So also running the multiple RV results through different coding packages, we are able to determine the systemic velocity and also the semi-amplitude of the RV. So as you can see here, this spectrum is subtracted out by the systemic velocity. So basically, the changing velocity here is purely caused by the rotation of the planet. And as you can see from the right-hand panel, we can determine the semi-amplitude of the RV based on that figure. So with all these observational data, we are now able to calculate some stellar properties and planet properties as the main results in this paper. So using the radius and K-band magnitude relation, we are able to calculate the stellar radius using the binomial relation shown here, where the x is representing the K-band magnitude and y is representing the stellar radius. Also, the mass of the planet of the star TOI-2136 could be calculated using the mass and K-band magnitude relation, illustrating in this equation, where AI it is a fitting coefficient and the n is the order of the fit, and where the ZP is the 0-point magnitude. So the only two unknown quantity, or like we can calculate it from the equation, would be the stellar mass or the K-band magnitude. So in this case, the K-band magnitude is known, so we can calculate the mass of the star directly from this equation. So further, to build on independent transit and RV results, a joint fit model was applied to determine the properties of TOI-2136b, the planet. So multiple coding packages were used to simultaneously model the environment and the data obtained both on the ground and in space. So using the joint fit model, TOI-2136b has a radius of 2.19 Earth radius and a mass of 6.38 Earth mass. So from the results, we can see that it is a relatively small planet. And comparing to the condition or the properties of the host star, we can conclude that it is a small planet orbiting a low mass star. And to further study the composition of the planet, we compare that to a two-layer internal structure model presented on the right-hand side. So as we can see here from the location of the planet, it lies between the 100% water and the 50% water line, and it is much closer to the 100% rock line compared to the cold helium or hydrogen line. So basically, we could infer that the planet is either a rocky planet with atmosphere or a pure water ice planet. So as the last piece of the conclusion and the most important knowledge we want to get out of this discovery is the location on the radius versus period plot, since it is related to the location of the radius value. So as you can see here, based on the period and the radius determined from the observational data, we see that the planet TOI-2136b is located slightly above the radius value for low mass dwarf predicted by the photo evaporation model. So this is the final piece of conclusion in this paper. And personally, I think it's very interesting due to the fact that it falls into the small planet orbiting low mass star category, but it's even closer to the model predicted by the photoevaporation model, which is suitable for planet orbiting a sun-like star. But as I just said in the previous presentation, the dominant mechanism is still unclear and it's an ongoing discussion topic. So we can't reach a conclusion on which is the dominant mechanism. So especially in the low mass region. So we're just hoping that the discovery of this planet system would help to populate the small sample population of small planet orbiting low mass star, and hopefully the answer would be revealed soon with more and more sample population being discovered. So thank you for your listening, and here is a list of references if you're interested.